Hello everyone, we are Team MAWU. Let me first introduce our objective. Our objective is to create a test input generator that can quickly generate diverse valid test inputs with the use of reinforcement learning. Programs have bugs, and the only way to find those bugs is to feed the program with a huge number of diverse inputs. However, doing so is not that easy. In the past, it was okay to generate random sequences of characters, and at least some of them could reveal meaningful bugs. Yet now the programs are more complicated and fortunately more robust to these kinds of random inputs. And many programs nowadays have strict input constraints, like Mozilla Reno takes only JavaScript inputs. Thus, random sequences of characters will not reveal any bugs. So these days, generator-based fuzzing is widely used. Generator-based fuzzing basically tries to produce test inputs that satisfy the input constraints of the program. Therefore, they are more successful at finding bugs than completely random generators. However, this approach uses white box or gray box testing. That is, they use internal information about the program, such as source code, and during the execution of the tests, they use coverage information of individual test inputs to optimize the test generators. Nonetheless, this can be rather slow, and it limits the speed at which tests can be executed. For that reason, we propose a solution that uses black box testing, which does not use any internal information about the program. Let me explain it better with an example. To note, most complex types of inputs can be expressed using a binary tree. And in this example, assume that our program accepts only binary search trees. And this is a random binary search tree generator. And this is the program that accepts only binary search trees as an input. And as you can see, the assume statement rejects all inputs that are not valid binary search trees. In this example, you can see 3 choice points where decisions are made. First, you choose a value, then you can go to the left child, or you can go to the right child, and everything continues recursively. If the first value is, for example, 8, and we continue through the right branch, then the valid values for the right child can only be either 9 or 10. However, in this random generator, it still chooses between 0 and 10, which means that there is less than 20% chance of choosing the values of 9 and 10. Thus, due to these situations, this random binary search tree generator will produce very few valid binary search trees. That means very few valid inputs for the program. To solve this issue, we propose to use black box approach to automatically guide the generator into generating diverse inputs that satisfy the input constraints. We're going to use reinforcement learning, specifically Monte Carlo control, to fine-tune the choice parameters at points where the generator decides what actions to take. At every choice point, the decisions are made by the Q table that uses states, that is, basically the history of all past choices made at these points, these choice points, and the information about which generated trees were accepted by the program and which were not. That's why action points are constrained at specific points so that the resulting test input can pass the input constraints of the program. However, this approach is not perfect, so it has some shortcomings. First, this approach uses Q tables at every choice points to decide what actions to take. This can become really slow for more complex test generators with many choice points. To tackle this issue, we plan to use deep neural networks instead of the Q tables to decide the actions. This should allow larger choice spaces that can facilitate more complex test inputs. This approach also tends to generate test inputs that are slightly biased. To reduce this bias, we intend to implement Monte Carlo control such that it forgets some of the old moves, which can improve the exploration of the generator. We will also attempt to find more optimal hyperparameters that can possibly boost the performance and increase the coverage of the test generator. So, how are we going to evaluate the success of our project? We will use real-world benchmarks such as Google Closure Compiler and Mozilla Reno. In particular, we focus on the following research questions. Does a rel check find many diverse valid inputs for real-world benchmarks? Does a rel check achieve better coverage than random algorithms when the input constraints are strict? Does a rel check find valid inputs faster than other approaches that use white or gray box information? Finally, I want to mention that it is an attempt to replicate and possibly improve the test generation technique proposed in the paper, called Quickly Generating Diverse Valid Test Inputs with Reinforcement Learning. Thank you and have a nice day.